In this video, we're going to discuss what's known as the second order forced harmonic oscillator. So we're going to go back to the spring mass system. This is a second order linear differential equation, m times y double prime plus b times y prime plus k times y. Now you may recall that we have a spring, and k is the spring constant, which measures how stiff it is. We're assuming that the system is damped. There's a certain amount of friction, so that's what B represents. And M represents the mass of the spring. So if you want to think about this as a mass moving back and forth like that, this is the situation. And the stiffer the spring, the more the thing will come back to equilibrium. So this equation is homogeneous because if we get all the y terms on one side, we have a 0. And you may recall that we can actually express the second order equation as a system, and we've done that several times. So if y denotes the displacement of the spring, we can let v denote its velocity. So v is y prime, which means that v prime, which is the acceleration, is the same as y double prime. So if we take this equation and if we solve for y double prime and divide everything by m, that means that y double prime, which is v prime, would be minus k over m times y minus b over m times v. That means we can express this second order equation in matrix form in this manner. 0, 1 minus k over m minus b over m. If we expanded, for example, if we took 0, 1, multiplied it by yv, we would get v. That has to equal y prime, which we know to be true. V prime would be minus k over m times y minus b over m times v, which is precisely this equation here. So we've looked at this equation from two perspectives, as a second order equation, but also as a system involving a matrix. Now the standard approach for solving one would be to use the guessing method. We would substitute y equals e to the st into this equation, and we would find the two values of s1 and s2 that make y of t a solution. If we do that, we're going to assume that S1 and S2 are different. Then we can figure out what S happens to be. So let's assume for a moment that M is 1, B is 4, and K is 3. So that means I substitute 1 in here, I substitute 4 in there, and I substitute 3 in there. And then using our guessing method, we get two values of S. S1 is -1 and S2 is -3. So that means two solutions to this equation up here, would be e to the minus t and e to the -3t. Now, one of the things we've also seen before is that if we were to substitute these values of m, b, and k into this matrix and determine the eigenvalues, those eigenvalues are -1 and -3. They coincide with S1 and S2. And that's something you established in a previous homework problem, I believe. Now, the superposition principle also holds for this equation, so that means that if y1 and y2 are solutions, so is any linear combination of the two. And if we know y of 0 and y prime of 0, the initial displacement and the initial velocity, we should be able to figure out what C1 and C2 are. So let's take a look at an example. Let's suppose that the initial position of our mass is 2 and the initial velocity is -2. So in this case, we substitute 0 in for t. That's going to give me 2 equals C1 plus C2. If we take the derivative of this, we would get minus C1 e to the -t minus 3 e to the -3t, which is right there. And if we substitute 0 into that, we would get minus C1 minus 3c, minus C1 minus, I believe that should be a minus. And we want that to be -2. And if we solve this system, we would get C1 equals 2 and C2 equals 0. Let's check that out. Okay, so if we substitute 0 into this, we get 2. If we take the derivative and substituted 0 in, we would get -2 as well. And this is also a solution of the equation when m is 1, b is 4, and k is 3. Now what happens, let's say m is 1, b is 4, and k is 13. Now we have a very much larger k value, so the spring is much stiffer. If we do the same approach as we did before, substituting e to the st into our differential equation, we would get two roots, but now they are complex roots. Minus 2 plus 3i and minus 2 minus 3i. They are complex conjugates of one another. So that means that the first solution would be e to the minus 2 plus 3it. Now this is a function that can be broken down into its real and imaginary parts if we use Euler's formula. More specifically, if we take e to the minus 2 plus 3it and expand it, we can use Euler's formula to write it as e to the negative 2t cosine 3t, e to the minus 2t times sine of 3t. Now this whole thing is a solution, but just like what we did for systems, this part and this part, the real and imaginary parts separately, are also solutions. And we can tell that we could actually substitute this into the differential equation. This differential equation, using these values of m, b, and k, we could actually substitute them in and check. So that means we have two solutions, e to the negative 2t cosine 3t and e to the minus 2t sine 3t. Now again, we got those by using the one complex value minus 2 plus 3i. We didn't have to use the other one. We substituted this in and broke things down into the real and imaginary parts using Euler's formula. So that means that this is a solution, as is this. The general solution is going to be any linear combination. And if we know y of 0 and y prime of 0, in other words, the masses, initial displacement and initial velocity, this allows us to compute C1 and C2. Now, notice that we never used minus 2 minus 3i. This is kind of like when this system had complex eigenvalues, we only needed one of those eigenvalues. Now, the forced harmonic oscillator arises when we introduce what's known as a forcing term on the right side of 1. So like a spring mass system, this is sort of like the non-homogeneous system. Oopsie. Now being applied, now the differential equation is non-homogeneous. So our differential equation looks like something like this. Now the f of t might be like a sine function, it might be a constant, it might be, let's say, an exponential function. So I want you to think about it like this. You have a spring mass system, but you have someone who's applying an external force. That external force might be exponential in nature, it might be sinusoidal in nature, but someone has come in and has the audacity to start applying a force to your system. So just like to your spring mass system, just like we did for systems, we're going to break things down into two parts. We're first going to solve the homogeneous equation for y1 and y2 and assume that they're not scalar multiples of each other. That means we're simply going to replace f of t with 0 and solve just like we did a few minutes ago. And then what we're going to do is we're going to find a particular solution to this. And the general solution to this is going to be the general solution to the homogeneous, which is that, plus our particular solution to the non-homogeneous. And then we can use initial values of y and its derivative to figure out C1 and C2. So the big question is, how do we figure out what that particular solution is? Well, we use kind of a guessing method. To find the particular solution, we use a tool known as undetermined coefficients. We look at our forcing term. And the forcing term could be a constant, it could be sinusoidal, it could be exponential, it could be all sorts of things. And depending upon the type of form of the forcing term, we guess that y sub p takes a particular form as well. So this is kind of a summary, and we're going to do some examples in a moment. If our forcing term is exponential, we make a guess that our particular solution is exponential. If our forcing term involves sines and cosines, like sine of 5t, we assume that our particular solution takes this form. And we do a similar thing for polynomial. So let's take a look at a particular example. Let's suppose we have an equation where m is 1, b is 4, k is 3, and f of t is sine of 2t. So this means that someone is coming in and exerting an external force that is sine of 2t on our system. So in other words, we're looking at this. So the first thing we're going to do is we're going to replace the sine of 2t with a 0, and we're going to solve the corresponding homogeneous equation. And we did that on the previous page, and we got e to the negative t and e to the negative 3t. Now, to find a particular solution, our forcing term is sine of 2t. So what we're going to do is we're going to substitute a particular solution excuse me, of the form a cosine of 2t plus b sine of 2t. And we're going to try to figure out the values of a and b that make things work. So we're going to take this, we're going to take its first derivative and its second derivative, and we're going to substitute it into this equation. Now the first derivative of this would be minus 2a sine of 2t minus or plus 2b cosine of 2t. That's by the chain rule. If we took the second derivative, we would get minus 4a cosine 2t minus 4b sine 2t. You might want to pause and just check that calculation, but if you took the derivative of this, you would actually get this. Now what we're going to do is we're going to substitute this into the left side of the differential equation. We're going, wherever we see y double prime, we're going to substitute this in. Wherever we see, this should be y prime, my apologies. This should be y prime. Wherever we see y prime, we're going to substitute that in here. And wherever we see a y, we're going to substitute this in. And we're going to combine the like sine and cosine terms. So let's do that. So yp double prime is that plus 4, and that should be yp prime. Here's yp prime. So again, yp double prime, yp prime plus 3 yp. Now, if I simplify this, if I look at all the cosine terms, I have minus 4a of them there. I have 8b of them there. And I think I get the others to cancel out. So let's check that again. I have minus 4a. Okay, so minus 4a. And then I have plus 8b right there, times cosine of t. Now let's look at our sine form quantities. We have a minus 4b, minus 2a, actually minus 8a, and then we have 3b. So if I have 3b there, and if I have minus 4b, I have minus b. And then I have a minus 8a, which goes right there. So you might want to check this, but if you were to expand this and collect all the cosine and sine terms, you would get this. Now, take a look at this. When we go back to our differential equation, we want, when the dust settles, we want that to equal sine of 2t. In other words, we want this whole thing to work out to be the sine of 2t. Well, the way to make that work is to set this to 0 and to set that to 1 and figure out what values of a and b make that work. So we set minus a plus 8b to 0 and minus 8a minus b equal to 1, and we solve that system for a and b. And I'll let you check on your own. If you solve this equation and that equation, you get for a minus 8 over 65 and b is minus 1 over 65. You might want to check this on your own. So that means our particular solution is minus 8 over 65, that's a times cosine 2t, plus b, which is minus 1 over 65 sine of 2t. So our general solution is given by the solution to the homogeneous plus the particular solution that we just found above. And if we knew initial conditions, we could figure out y of 0 and y prime of 0. And similar approaches would work for other forcing terms, and we will practice this subsequently. Let's suppose on the other side of the equation, instead of a sine term, we had a e to the 2t. So now as someone is applying an exponentially growing forcing term, we would substitute a e to the 2t into for y sub p and see what makes things work, because our forcing term is exponential, so we'd substitute something like that in. Similarly, let's say we had a polynomial forcing term. So our particular solution, we would substitute something of the form at squared plus bt plus c into our differential equation to figure out what values of a, b, and c would work. And we will practice this in class.